Now we are ready to study the most probably wonderful application of gamma functions, and this is the computation of infinite products. So this is our infinite product, and probably the first legitimate question you may ask is why it assumes such a form. Well, this deals with the convergence. So let's first study just a little bit the general formula that's infinite products and their property, and especially the conditions under which they converge. So suppose we have the following infinite product. Usually it's written in the form 1 plus an, like that. So why? Well, because when you multiply term by term, and you see that in order the whole thing to converge to something finite, you want every term to become closer to unity when n goes to infinity. So in the end, an should go to 0 when n goes to infinity. And this is their necessary condition for the infinite product to converge. Later on, we'll study their sufficient condition. Okay, so now let's address our infinite product which we have here. But before we do so, let's first remind just a little bit how to deal with finite products and the small little trick which we studied when we addressed the Legendre's duplication formula. So here is the product which we are going to deal with. So it's, say, a times a plus 1 times a plus 2 times, finally, the end term is going to be a plus n. So how can we simplify it? As I explained earlier, you should multiply it by the gamma function of a and divide it by the same thing. So and then it starts to convolute. For example, gamma of a times a will give you gamma function of a plus 1. Then you convolute gamma function of a plus 1 and a plus 1 to get gamma function of a plus 2. So it's a chain convolution. And finally, in the end, you will get this gamma function of n plus a plus 1 divided by the gamma function of a. Okay, so we'll need it in a second. Now let's simplify our product. So pi of z. So what we're going to do, we are going to actually expand this product into an just infinite product. Okay, let's do this. So first of all, let us rewrite it in a more suitable way. So we put n squared in their denominator, like this. Then we expand the denominator, like n plus iz times n minus iz, divided by n here and n here. And then let us make the full expansion. So it's a limit expression, so we put a limit sign here, and here we go. So instead of the first fraction, we will actually write down the full expansion. Okay, here we go. So the first term is going to be 1 plus iz. The next term is going to be 2 plus iz, and so on and so forth till we arrive at the final term, which is just n plus iz, and divided by 1 times 2 times n. So this is the first fraction. Of course, there is a second one. which is basically the same. You just change iz to minus iz. All right. And now let's transform that kind of product according to our simplification rule. So because you see this this product which we have here is precisely of the same form as we just addressed here. So A here is simply 1 plus iz, and so there are n minus 1 terms, and in the end what you will get is simply, okay, let's rewrite it. So instead of this product in the denominator, you'll get gamma function of, well, n plus a plus 1. But instead of a, we plug in 1 plus iz. Instead of n, we plug in n minus 1 because there are n minus 1 terms. And plus 1 divided by the gamma function of a, which is 1 plus iz. Then there is this factorial 1 times 2 times n, which we will rewrite as gamma function of n plus 1. Okay, so this is the first part of our product. And here comes the second one. So the only difference is that we change iz to minus iz. Okay. All right, and by the way, here 1 and minus 1 cancel each other. Okay, so the second part is going to be just gamma function of, let's see, it's going to be 1 minus iz plus n divided by gamma function of 1 minus iz and gamma function of n plus 1. Okay, and this is way more suitable expression to work with. All right, now to progress further, let's prove one more beautiful and very useful identity, and this is their identity itself. So let's prove that. Let's actually highlight it. So let's prove that the gamma function of a plus n divided by the gamma function of n behaves as n to a when n tends to infinity. Okay. And to prove it, we need to use the asymptotics which we just discussed. So gamma function of a plus n. So this is just simple Stirling formula. It's 2 pi divided by a plus n times n plus a over e times n plus a. So this is the first asymptotics of the gamma function of a plus n, and below we put the second one, which is 2 pi by n times n over e times n. Well, first of all, let's simplify these square roots. So obviously we see that 2 pi and 2 pi, the denominator and denominator cancel each other, and we can factor out n, and in the end, so it just, okay, let's put it like this. So it's going to be 1 over 1 plus a over n times, and then we need to simplify these power expressions. Here they are, right? So the best way to simplify them, well, is usual. We just need to rewrite them in the exponential form. So let's do this. So the first term is going to be, all right, it's n plus a times log of n plus a. Right, and then minus n minus a. So this is the denominator, and then the denominator, which is obviously minus n logarithm n plus n. Okay, now let's look at the root term. So when n tends to plus infinity, the root term obviously gives you 1. Now let's work a little bit with the exponential. Well, it's just standard. What we do, we just make a Taylor expansion of the logarithm here. And, okay, let's do this. And finally what we get is n plus a. So the expansion of log gives you logarithm of n plus a over n. This is the first Taylor term. Then, okay, minus n minus a minus n logarithm n plus n. Okay, and now we cancel everything, so it's like minus n and n. Okay, well, the rest is not so obvious, so let's actually expand it. So exponential of n logarithm n plus a plus a logarithm n, sorry, okay, like that, and minus a minus n logarithm n. All right, so and finally we see that most terms cancels, and we are left with just the exponential of a logarithm n, which is nothing, right? Finally, we are ready to make one final step and to assault our expression for the pi of z. So we substitute, instead of the ratio of gamma functions, we substitute n plus 1 to iz divided by the gamma function of 1 plus iz. So this is the first fraction, and the second one will give us n plus 1 to minus iz divided by gamma function of 1 minus iz. Alright, and now we see how the whole thing converges, because we have n minus 1 here. Let me highlight it for you. So we have n minus 1, n plus 1 here to iz, and n plus 1 here to minus iz. So in the end, you will get n plus 1 to 0 power. So this was the principal source of divergence of this infinite product, and now, just like a miracle, it cancels, and the only thing which is left is the product of two gamma functions in their denominator. And now we can use the mirror relation to simplify this product. So we have 1 in the denominator. Now instead of gamma function of 1 plus iz, let's rewrite it using our factorial rule as iz times gamma function of iz. And this is a very suitable expression for the application of the mirror relation. So finally, it's simply 1 over iz. So instead of this product, we plug in pi over sine I pi z. And now you remember that this sign of the imaginary argument is simply sine hyperbolic of z multiplied by I. And as a result, we get the final answer for our infinite product. So it's sine hyperbolic of z, of pi z, of course, pi z, divided by pi z.